the topic. By and large, laminar and turbulence of flow, streamline flow is called laminar, and turbulence is when some eddies, some unidirectional motion occurs, and this turbulence is accompanied by specific sound generation, which is the basis for measuring blood pressure. In case of circulation, the turbulence occurs if the travel speed is much higher than the so-called critical velocity. So next time we will study a formula, but let me write it today as well. The formula for critical velocity, the velocity above which the flow is turbulent and below which the flow is laminar. So thus, let me write the formula for the critical velocity, which we'll discuss next time as well. So thus we've got critical velocity, which is directly proportional to the viscosity, inversely proportional to the density of fluid and radius of the tube. R is a constant that is called Reynolds number. So Reynolds number being a criterion for the type of flow, whether it is critical or laminar. If velocity is bigger than critical, this suggests turbulence. So if it is less, then we've got laminar flow. And in the aorta, we will next time even will calculate what would be the blood speed in the aorta as the blood leaves the right ventricle, and there is the velocity is high enough to produce turbulence there. But turbulence also may occur if there are deposits. Suppose this is some vessel, blood vessel, and as a result, some part of it, as a result of deposits formation, atherosclerotic plaque. So then we would observe what? Narrowing of the lumen, which will make velocity bigger and above the critical velocity, and then turbulence will occur. So let me, I omitted this in fluid dynamics. The so-called continuity equation is important. Continuity equation says that the product of cross-sectional area and flow velocity stays same in every part of a tube, which means that if the cross-sectional area, as in case of constrictions, decreases, then the velocity increases for the product to stay same. Continuity equation. This is called continuity equation. And turbulence by and by itself, it is considered as an initiating stimulus for atherosclerosis, which we'll study more in biophysics when we discuss the free radical genesis of atherosclerosis. We will, as I've told you, calculate next time pressure drop across blood vessels. Also, we will calculate critical velocity in aorta. Deposits and constrictions being mentioned here, which I I explained. So by and by, let me see here. So the question important was, is it possible to apply Poiseuille's law in the study of blood? Since given here, blood is not pure liquid. Pure liquid means liquid as water, in which viscosity does not depend on pressure. In case of blood, it is complicated. It contains not just proteins, but different other compounds being dissolved, but also blood cells, and specifically red blood cells being their number being greatest one as compared to the other blood cells, and when the pressure increases, then those blood cells may accumulate along the axial part of the tube, thus decreasing viscosity, which means that the viscosity in the Poiseuille's law cannot be considered constant, especially when the pressure is high. However, as we'll discuss next time as well, within normal blood pressures, Poiseuille's law can be applied, having in mind specific characteristics that need to be taken when discussing this approximately constant in the normal range of blood pressures for the Poiseuille's law to be applicable. Increased accumulation of red blood cells, I explained this. And now I would like to consider, it is a separate topic in the synopsis, erythrocyte sedimentation rate. And then if there is some time, we may consider factors contributing to the volume flow rate. Okay, let us come back to quickly to the erythrocyte sedimentation rate. So it is measured in this simple way. We've got some in clinical. Okay, I hope that you can see. In this simple way, in clinical laboratory, we've got vertical tubes in which after manufacture, blood is placed, and the settling of blood cells is observed, and how much is this within specified time. All those things are measured to find rate. What is it? Rate. Rate is a change in distance over time of velocity of settling. This is erythrocyte sedimentation rate. No specific parameter, indicator of inflammatory condition. No specific, but useful. So in this text, it is given. It is an indicator of some inflammatory condition in response to some tissue injury due to the acute phase proteins being produced and suspended in plasma. Some acute phase proteins mentioned here in the text as well, which result in the change in the parameter. And I want now to derive the formula which can be used to quantify and to calculate and to see the factors determining erythrocyte sedimentation rate. So you can see verbally the factors which are very well observed in the equation.
So let me switch on the board, and so we've got blood being allowed to fall in response to what? To gravity, which means that if this is a tube, to consider some tube, vertical one, and I'm going to consider just a single erythrocyte. So let us consider its shape spherical. You know that this is an approximation. And what are the forces being experienced? We've got weight of the erythrocyte. Since it is suspended in plasma, it experiences Archimedes force, but also there is a force of friction, which we wrote previous time, and it is called Stokes force, according to Fs, according to the Stokes law. So thus, after putting the blood in the tube, due to the weight, erythrocytes begin to settle, and as they move downward, frictional force increases as well, and after some time, very soon, the motion becomes uniform. Uniform motion means what? With constant velocity and zero acceleration. So